Let's go ahead and get started. It is good to see the quiet, sleepy classroom today, and I understand that. Um, where we left off on Thursday is we were looking at primitive assembly, kind of as a either algorithmic approach to it or sort of like a state machine approach to it, and we didn't really come back together as a class and kind of share results, but I did see teams that were seemingly coming up with good solutions, both for their lab as well as what we did in class. I think the tricky thing about this is not the algorithms themselves, which I think are pretty straightforward for how to take a triangle strip and emit triangles from it. I think just testing it in hardware is going to be a little tricky for each of the teams because it's just really hard to know that you have a successful result. In simulation, it should all look fine, well, and good, but until you're actually doing the rasterization and the filling of the triangles, it'll be really hard to visualize that you're getting the results back out that you want. So, teams that have made progress on the primitive assembler as part of MP2, that's great. If you're just doing the triangles part, that's also probably sufficient for now because you do have a lot of testing for each triangle in isolation, and then the assembly is kind of a complementary piece to that. So let's look at it from the perspective of, as we're progressing our way through the pipeline here, we have this kind of pipeline view from vertex fetch called assembly here to the transformations of which we're doing very few of so far, to the primitive operations, and now to finally that rasterization step. And we've used that term a lot, and this is the primary focus of this learning module. It's figuring out what is inside that primitive, what fragments should be generated associated with that primitive, and what their attributes should be. And you can definitely think of the primitive as, of the vertex at this point of having some sort of attribute data structure associated with it. We do it in our own specific way in the labs, but in general, you have some sort of data structure associated with it. And the point of the rasterization stage is given a position in an XY coordinate system, determine a position in an XY coordinate system for the vertices that have all the other attributes defined for it. So we have green, green, red vertex here in our triangle strip. Determine what all the attributes of the individual generated fragments should be uh, for those assembled primitives. And it's easiest to visualize it with color, right? It's easiest to see the attribute values being interpolated as we rasterize for our color. But the truth is, it applies to all of the attributes. It's hard to see depth information and normals and things like that. But we would be doing this rasterization for all of those. So we have to figure out what should be a fragment or not. What are the candidate fragments for a given primitive, and what should their attributes be? You're doing that in MP2. We're going to do that today. We're going to start with lines, but it's really the same exact approach, and I think you'll see that as we walk through that here today. Um, Arguably, this is, I don't know, sixth grade math that we're doing today, and maybe a good refresher in sixth grade math for some of you, and that's okay. It's basic math. I think what we do is we take this basic math, and we try to appreciate how we really try to minimize the amount of computation that's happening. It's nothing you certainly can't do with pencil and paper, right? You did that for the pre-lab for MP2. Now, when we're building hardware for it, we really have this laser focus on minimizing the amount of operations and the type of operations that are required. So you always kind of see this trade-off in graphics hardware where the math, I guess it goes beyond sixth grade level eventually, but not that much far past it, right? You don't really even get to college math for most of this. And we would look at that and say, okay, this is how we could do it offline or with a calculator, paper and pencil. How do we do it efficiently in hardware? And rasterization is an early and kind of a classic example of exploring that trade-off between not necessarily accuracy and resource efficiency, but maybe how we implement something with as much resource efficiency as possible. So we're going to start with lines here. So that's a line. We can define a line by any two endpoints here. That's our line segment, and you can think of these as vertices to describe a line, or just think of them as a line in an abstract sense here with two endpoints for our line segment here. And what will generally be the case if we have our pipeline in this sort of organization is that our primitive assembly and our rasterization is going to happen after all the vertex transformations. I reordered the content here from how maybe others would present it. We haven't really talked about vertex transformations, but we have implemented one of them already in lab. So the viewport transformation is a type of vertex transformation. We're taking our vertices as they come in with x, y, and z value in that normalized device coordinate space, -1 to 1, and we're converting it to screen space. We're converting it to a space in which our values for our x and y, if they're not integers themselves, because they could still have some fractional components, they are corresponding ultimately to positions relative to either a screen, a display, or a window inside that screen. So it's perfectly appropriate and a natural way to think about what we're doing for rasterization and be thinking about our vertices as having these integer values associated with them. So this is not a synthetic example in that sense. There may still be some fractional component here, but we can also do rasterization assuming viewport transformation has been applied. We maybe do some truncation or some rounding, and our line segments in this case have vertices that are all just integer components. So we know how to do that with pencil and paper pretty easily, right? Get out your graph paper, fill in 2 comma 2 and 7 comma 5, and just get your ruler out and draw between them, right? But what does that look like when we do it on an actual display, right? Where we have these pixels, right, which are sort of a discrete sample of what's intended to be a continuous image. We see the side effects, we see the impact of having that discretization, right? That ultimately we have this nice straight line we're wanting to render, or a triangle we're wanting to draw here, and we have to make decisions. And there's a lot of different decisions we can make, and we'll talk about a lot of them over the course of this learning module. But there's decisions we have to make ultimately between for our continuous view of what we want to draw. We want to draw a line, a continuous concept. What does that mean in our discretized space here? It's a pixel, ultimately, that we're turning on or turning off, or color we're setting to red or less red. We'll definitely talk about anti-aliasing, but that also gets into some fairly advanced topics as well here. But we have that trade-off of, if we're not doing any anti-aliasing, do we turn on the pixel or not, corresponding to the decisions we make along the way. So these line rasterization algorithms, that's really what they're attempting to do. This is for what we know. We know the 2 vertices that are our endpoint, and we know other things about them, not just their position, we know all the other attributes. So it's one thing to say anti-aliasing for turning on a pixel or not, but then there's all the other attributes we're doing as well. So everything can be thought of as a line as we're interpolating between 2 attributes, between 2 endpoints here. Could be all the other things that we also store associated with our vertex. It's just easiest to visualize it as a 2-dimensional line being drawn here. So we have that fundamental trade-off. So a very brief review of the, 6th grade math. I don't know, whatever grade this is. There's lots of ways we can represent a line. The most basic way, a very fundamental way, is to use so-called slope-intercept form of the equation, right? Your y equals mx plus b. If you don't remember that, that's okay. But that's, given 2 endpoints, we can find the rise over the run and calculate our slope, and then we can plug in any known point and then also calculate our y-intercept. So m is our slope here, and b is our y-intercept. So we know that is the equation for a basic line, or one way of representing the equation for a line. And our slope can take various values, right? And we know that for a slope of m equals 0, that is a horizontal flat line. For a vertical line, we can't differentiate. We have a slope of infinity there. And then just some example slopes that we have, right? We have slope of m equals 1. For every plus 1 in the x dimension, we also then get a plus 1 in the y dimension, and for all the other possible values here. So one approach we could take for doing line drawing, for rasterizing a line, is given 2 points, right? Given the equation for a line, which is just the known vertices of 2 points, we could just plug it in to the slope-intercept form of the equation. We can do that. I mean, we can. And we should be able to sort that out as a class here. Okay, I'll do it. We'll do it together, so you don't feel that you're wasting your time here. But okay, so given 2 known points, if I can get my pen here to work properly. Okay, so given that we know 2, 2, and what was the other one? 7, comma 5. That's my attempt to draw a point there. 2, 2, and 7, comma 5. And we have to figure out the slope, for example, right? We have a rise of 3 and a run of 5, so our slope is 3/5. And if I got that wrong, I know I won't hear the end of it. And we can then plug in, given y equals mx plus b, any point that we know, and we know 2 comma 2 is a valid point. So we get 2 equals 3/5 times 2. We get our intercept is 4/5. So we have the form of that equation. So y equals 3/5 x plus 4/5. So one valid way to rasterize this line is literally just to work out what the x value for a given x value, what the equivalent y value should be. And I think you'll see the first issue, but we can come up with an easy solution for it. So y equals 2. We plug in 2 to that equation. We get a 10/5. We get 2. Of course, that's our initial point. We plug in 3. So y of 3. That's 3/5 times 3 plus 4/5. Uh, that's 13/5. That's 2 and 3/5. So we can't draw ultimately on our display. We can't draw something at least by default at 2 and 3/5. Perhaps we round. So 2 and 3/5 is closer to 3 than to 2. We round that. We get a value here. Someone asked about, with higher resolution, is this issue of aliasing an issue or not? Well, it's a relative thing, right? It's an issue, but it's maybe less of an issue. But then, as you want more fidelity in what you're trying to draw, you'll still be able to see the issues of kind of the jaggedness of the edges of the line that you're drawing there. Um, where we were at. Okay, so that's y of 3 is equal to 2 and 3/5, right? We then plug into 4. We get 3/5 times 4 plus 4/5. That's 3 and 1/5. So we would get, rounding back down to 3, we would get a value. I keep erasing stuff for some reason. We get a value there. I'm just pressing it too hard. This is lovely. There we go. Plug in y of 5. That's 3/5 times 5 plus 4/5. That's 19/5. That's 3 and 4/5. We then round up to 4. And finally, we plug in 6. That's 3/5 times 6 plus 4/5. That's 22 over 5. That's also just 4, right? That's 4 and 2/5. Okay. So that approach worked. I mean, that approach is perfectly valid, right? Given the equation for a line, um, something didn't entirely draw here. It looks like we lost 1 point here still. We rounded up to begin with, right? At 3. Okay, that one got erased. All right. So given an equation for a line, there's nothing stopping us from just plugging in that equation for a line and rounding or truncating or making some decision how we're going to kind of finally get back out to a discretized value for it and getting our line back out that way. That's not wrong. It's not an incorrect approach. And that's what this slide is just showing. Yeah. So we plug it in, we round it off. Um, the downside, if we want to call it that, and I got to be a little bit careful with the phrasing here, where it says, this approach is just way too slow. Well, way too slow is kind of a relative thing. I think a more precise way to phrase the downside of this approach is not necessarily the speed argument, which is a bit more fuzzy nowadays. It would be more of, what would our hardware realization have to be for it? So we would have to, first off, calculate M, calculate B, given the two endpoints of a line. And then, given that slope would likely be, a fractional value, do some sort of floating point multiply accumulation for each point we want to plug into it, as well as some rounding ultimately for our x, y coordinates. So it's not way too slow, but the hardware realization for that would be non-trivial, right? And certainly, when you look at the history of computer graphics, as I mentioned, going from basic arithmetic approaches to trying to simplify what hardware is required is a pretty fundamental part of that. So not necessarily too slow. We could build a pretty fast thing to do that, I would think, nowadays. Fast is relative anyway. But certainly in terms of our hardware realization, not just calculating M and B, but plugging that in for every single point is going to require a lot of floating point arithmetic to be able to do that correctly. So a very quick point about slopes, and I'm gonna bring this up and just kind of ignore it for the rest of it. That we calculated our slope as y as a function of x, right? There's nothing that requires us to do it that way. We also could have calculated the slope of x as a function of y, or rewritten the function of x as a function of y, and you could do run over rise, right, and done it the exact other way around. If we had done it for that line, where instead of having our slope of was it 3/5, instead having our slope be basically 5/3 that we're plugging in there, we could also have rasterized the equation using that approach. If we had plugged in that approach instead, and calculated our change in y given the slope in that dimension, the math is exactly the same. Let's be clear about that, right? It's an equally valid equation for that line, but the actual points we would have chosen, we would have only been filling in 4 points given the distance between 2 and 5, excuse me, in that y dimension there. We would only have been calculating 4 points, and the resulting line would not have looked as good. Independent of anti-aliasing and other approaches we could do to improve upon partial coverage of pixels and things like that, the line wouldn't have looked as good. So, given a slope of 3/5 versus a slope of 5/3, the approach that has a slope of 3/5 maybe gives us a better result here. And that kind of makes sense in the sense that, as we have larger and larger slopes, looking at the absolute values of the slope there, as we have larger and larger absolute values of our slopes, we're jumping more and more pixels apart for every increment in either the x or the y dimension there. So that is true. And so the same approach could be applied by looking at what the slope is and determining which way to interpolate is going to give us the more pixels to potentially fill in. So if we calculate m in our y equals mx plus b and get a value of 700 or something like that, right? Um, that's going to be a very large jump. For every change in x, we're going to have a change in 700 of y, and we're going to have a really partially filled in line. It's not going to look very good. But then that would give us a hint to say, well, we have such a very large slope in that dimension. Just take the inverse of that. Calculate x as a function of y, where you would then get a slope of 1 over 700, and then you get to fill in all those points. It's the same exact line equation. It's the same exact approach that's being followed, just based on whether or not the slope is very large or not, determining whether to increment in the x dimension or in the y dimension. I mentioned that now. This next approach I'm going to bring up for line rasterization also implicitly takes that into account, but it just doesn't say it so explicitly. So um, we are assuming then for our line rendering that our slope is between -1 and 1. Because if it's not between -1 and 1, we can always just invert the equation and wind up with a slope between -1 and 1, right? Even for our slope of infinity here, yes, that'd be very hard to apply that equation for, but that's the same as the slope of 0 in the other dimension, right? So we can always then just increment our y by plus or minus 1 and then get our change, which would be 0 in our x dimension for that. We I think implicitly do that when we take the ruler and we draw that line between the two segments, the 2 points of our segment there. The rasterization algorithm as implemented in hardware could also do the same exact thing. We can calculate the slope, determine the magnitude of that slope, and then determine do we increment in the x or in the y dimension as we generate our candidate fragments to be rendered here. So a different approach, or a somewhat complementary approach, and I'll start discussing it a little bit more slowly. Um, but the idea behind this approach, again, if we are assuming that our slope is between -1 and 1, or if we're just going in the upper right direction here, assuming our slope is between 0 and 1, part of the realization, and this should start to sound a little bit more familiar for those who really dug into and found bugs in our MP2 pre-lab. Part of the realization that makes this a much more tractable problem in terms of the hardware requirements is that okay, again, assuming our slope is between 0 and 1, we're going in the upper right direction, but not so extremely so. That when we go from xk to xk plus 1, when we're moving to the right in our line render, we're really just making a decision. For a slope between 0 and 1, we're making the decision whether to go up 1 in the y dimension or to stay flat. I think if I go back to the example that we were trying to draw on this slide, I think it'll still be there. Right? That's ultimately what we were doing. Again, that's assuming the slope was between 0 and 1. As we were going from our starting point to our ending point, we were incrementing x. Xk plus 1 equals xk plus 1. We're going up by 1 in the x dimension, and then we're determining, do we go up in the y dimension or do we stay flat? Sometimes we went up, other times we stayed flat. In this case, that just happened to be how it worked out based on plugging into the line equation and the slope-intercept form of the line equation and then doing some rounding. But in practice, that's always going to be the case, no matter how we want to do that calculation. Again, assuming that our slope is between 0 and 1 in this instance, we're choosing whether to go up 1 or not. And one decision factor that we can make is as we go from xk to xk plus 1, and we decide whether to fill in yk or yk plus 1, we would want to choose the one that's closer. That's what rounding was implicitly doing, right? by rounding, we were choosing which of those points was closer. That's what rounding does, right? If it's closer to the larger value, it goes up one. Otherwise, it goes down one in the integer domain, right? So that's what we're doing. We're choosing to basically to round. But in realizing that we're rounding, there's an approach, it's referred to as Bressenham's line algorithm, that allows us to do that rounding without actually having to calculate the actual floating point math itself. And this should start to sound pretty familiar as compared to our MP2 pre-lab. We're recognizing that as we go in the xk to xk plus 1, as we increment that by 1, we can calculate functions that tell us what the next result should be without having to plug into the original equation, which is always mathematically correct. It's just inefficient from a hardware resource perspective here. So just to belabor the point a little bit here, that distance, right? That distance between the quote unquote true value as plugged into the slope intercept form of the equation and whether we've chosen x or yk plus 1 or yk, that could be labeled as d upper or d lower. The distance from the quote unquote correct value y to what we would have if we rounded up, as well as that's d upper, and d lower is the distance between the quote unquote true value y and if we had stayed the same, that's our d lower. We know how to calculate this, but it turns out that we can actually figure out which one is larger, d upper or d lower, without having to calculate that y value each time. So that's given as follows, right? So d lower is y minus yk. So that's the space below the correct value of our line and the decision to stay exactly where we were, y sub k. D upper is the exact opposite. It's the upper value, the rounded up, which is the previous y value plus 1 minus that value of y. And we can plug that back into the slope-intercept form of the equation to get a value for d lower and d upper here. What makes Bressenham's line algorithm work, which is very similar to what we're doing in MP2, is, again, this looks like the same amount of math as before. We don't actually care about d lower and d upper. Try to make that point more clearly here. We care about them. We just care which one's larger, or we care which one's smaller, right? We care which way we should round. We don't actually care that it was 2 3/5. We care that it was 2 and more than 0.5 is really all that we're calculating for that approach, right? We need to know which direction is the more accurate one to go in for Bressenham's approach here. So we can take that into account and not actually have to calculate that 3/5. We just have to have a way to calculate which one of these values is lower. And you can maybe start to derive this yourself given that starting point. We don't actually need to know what d lower and upper is. We need to know which one's larger. D lower minus d upper. Is it going to be positive or is it going to be negative? And that's going to then tell us which one was larger than the other. So we can take that d lower minus d upper calculation. It simplifies the equation a little bit, but then we realize that, well, if d lower minus d upper, we really don't care about the actual value of d lower minus d upper. We care about the sign of that. Then that allows us to multiply any sort of value by it through it, and still the sign doesn't change when we do that multiplication. Again, we're assuming slope is between 0 and positive 1 for this to work, but the same math applies if we have negative slopes in the same. We can multiply that by delta x. That allows us to simplify the actual slope calculation that we would normally have to do. We've now gotten rid of that division entirely. We still have the intercept point here, which we can start to multiply by that to get a different constant c here. But now we can start to see that for a given xk, yk, we can determine what that sign is of the resulting d lower minus d upper by what will be a relatively easier thing to calculate than actually calculating the slope or the intercept in the first place. And this is what Bressenham refers to as sort of decision parameter p sub k. So for the kth step along the line, we can then define this decision parameter p sub k as that function of d lower minus d upper, as shown on the previous slide. We only care about the sign of that value, not the actual value itself. So given 2 points that define a line, we can very quickly, without having to do any multiplication or division certainly, calculate delta y and delta x. And then given x sub k, we're going to be able to do the calculation of the next p sub k without having to do very much calculation here as well. So that's the equation for the general p sub k. Given p sub k, we can then also calculate p sub k plus 1 to see how much that decision function is going to change from point to point. And then that's also just a function of xk plus 1 minus xk, as well as yk plus 1 minus yk. That seems to make the math more complicated, but then we recognize that xk plus 1 minus xk, as we're rasterizing our line and moving to the right, is always 1. So far, so good. And yk plus 1 minus yk is either 0 or 1 every time. We've either gone up 1 or we've gone up 0. So the actual change in our decision function as we go from point to point to point is changing by a very simple to calculate component. We have to first calculate p sub 0, and to calculate p sub 0, it's not actually shown here. We do have to plug it back into this equation for x0 and y0. But given a p sub 0, we can then calculate p1 very quickly based on whether the line has gone up or down and whether this is 1 or this is 0, given only delta x and only delta y. And this is all this is saying here. So xk plus 1, we're always going to the right by 1, so that part simplifies out significantly. And yk plus 1 minus yk is either 0 or 1, depending on what the previous decision was. Did we go up or down in our previous decision? So we initialize p sub 0, plugging it into that previous equation. And I don't show that, so take that as given for now. We plug in, we get our initial value of p sub 0. We have to calculate delta y, really 2 delta y and 2 delta x. And then as we go from xk to xk plus 1, we can very quickly determine the sign of our decision parameter without really having to do any multiplication at all. We did that pretty quickly. So let's walk through it. It may make more sense as we walk through it, and if it makes less sense, so be it. Let's rasterize a different line here. So give an example line that's going from 20, 10 to 30, 18. Let's blindly follow Bressenhand's algorithm and see where it gets us, right? We can calculate pretty easily those different parameters, right? So doing two simple subtractions, we can calculate delta x and delta y. And I know you're already saying, what if the slope is much larger? What if the slope is negative? You can always reorder the line and render in the right direction to get a positive slope from 0 to 1. So given a delta x, or given that line with those 2 points, we can calculate delta x, delta y, as well as 2 delta x and 2 delta y minus 2 delta x to get those values here. And then I didn't show the derivation of it, but you could plug it back into that equation 3 slides back. To get for p sub 0, you can get 6. So we can start with starting at the location of 20, 10. That's x0, or x0 is 20, y0 is 10. We can then, as we go from x0 to x1, which is 21, we can determine whether or not y1, or y of next, is plus 1 or not, based on the sign of that decision parameter. The actual value of that decision parameter isn't as important as whether it's positive or negative. Let's try to walk through it together. I won't split you into rooms to be able to do this. So here is our line for k equals 0. So for our initial point here, we have our values, and it might be easier to just write it on that slide. So we have 2 delta y minus 2 delta x, or just separately, 2 delta y is 16, 2 delta y minus 2 delta x is negative 4. So when we are going up 1, we're subtracting 4 from our p decision variable here. When we stay the same, we're adding 16 to that decision variable here. So let's write those down just so we don't lose them. And I don't have to keep going back and forth. So 2 delta y is 16, and 2 delta y minus 2 delta x is equal to negative 4. And I could write it down separately, but p sub 0 is our initial condition, is 6. Is 6. P sub 0 is 6. P sub 0 is positive, so our next value should be plus 1. We always know what xk plus 1 is. That's a given with how we're rasterizing it. So we can always write half of this if we're worried about getting this partially correct here. We always know the x parameter as we're going up. feel like I might have missed one. Anyway, fine. If I missed one, I missed one. Xk plus 1 is always xk plus 1. So we've gone up 1 in the x dimension. This decision value is telling us if it's positive, we also want to go up in the y dimension. So if pk is 6, it's positive. Yk or y0 is 10. Yk plus 1 should be 11. And filling this in hasn't really looked all that good. But there you go. We're kind of filling that in there. We next have to calculate p sub 1, right? P sub 1, let's go back to it here, equals p sub 0 plus that 2 delta y minus 2 delta x term. We've gone up 1, so we're going to change our decision value by this amount, by that -4. So the new value of p sub k would be 2. Still positive. It's getting close, but still positive. We've built up that much less rounding information as we've gone up 1 point here. So our next y sub 1 value, or y sub 2 value, the next value we're drawing here should be 12. Lost my nice line from before. Oh, there we go. X. X marks the spot. We went up in the y dimension again. Our next p sub k plus 2 is equal to p of k plus 1, or the next value as we increment along, minus 4 again, we get a p sub k of -2. We stay there. We don't actually go up. Next time along, we didn't go up, so this 2 delta x term is multiplied by 0. We actually are adding 2 delta y, so now we get 14. You can kind of see where this is going, right? We now have 14. That means we jump up on the next one. We're only going to drop by 4 each time, so we're going to keep going up. Until finally we get back down to our -4. And it kind of looks right? You know, in terms of whether we should be going up, it's doing the same exact thing. I guess it's blocked here. It's doing the same exact thing as our rounding. But instead of rounding, we're instead just determining whether we would have rounded or not as we plugged it into the original point slope equation, because that's all we ultimately needed to know. We didn't need to know that the value was 2 3/5. We just needed to know that the distance to 3 was closer than the distance to 2, and we would have rounded up in that case. I feel like I did something wrong here. You're supposed to call me out on those. Okay, it's actually -2 there, and we're back to 14 and 10 to get to 17 and 18. You know, whether you do that for the final point or not is immaterial. But that gives us the same exact points, at least. Whether these are good points, whether they should have been anti-aliased or not, the line algorithm approach gives us the same exact points. I think that's the more important part here, as if we had plugged into the slope-intercept form of the equation, without having to do anything other than just integer addition. Okay, so that's the trip. That's why Bresch and Hem's-Lang algorithm is considered, fundamental for computer graphics. I know we're not as interested in lines. We're not doing lines in labs, but basically, there's many such approaches to rasterizing triangles that basically treat it as a special case of rasterizing lines. The truth is, there are many such approaches to filling in triangles, and I've tried and come up with, I would say, conflicting answers as to today. You purchase a GPU today and install the latest drivers and everything. What the rasterization hardware looks like in practice, it's not that clear. I see conflicting reports as to what the actual answer is. So we'll learn the fundamentals. We'll be implementing our own. It's all going to be roughly similar. There's no new magic for it. There's different coordinate systems one can use that makes the math a little bit cleaner to do. But it's not going to be radically different from what we're learning. The exact precise way, to the extent that there is still fixed function hardware versus entirely using programmable shaders to do rasterization, is at least there's conflicting information regarding that. But algorithmically, at the very least, we're still doing the same basic thing. So this first approach is a so-called edge walking approach. And the idea of the edge walking approach is you walk the edges. The idea is that given a triangle, you can really think of it as being composed of three lines. And I'm pretty sure that if I asked you to design, a rasterization algorithm from scratch, you'd probably come up with something pretty similar to this. So this is a very appropriate approach to take. But the line or the edge walking approach is given P0, P1, and P2 that comprise our triangle, treat it as three separate lines. And in fact, draw the lines first. So to rasterize this triangle, use Bressenham's or whatever approach you use to first rasterize those individual lines and come up with a table or a set of values stored in memory corresponding to the locations along those lines. And given the slopes of those lines, you can do it such that you're not skipping any points. I know this looks like a very large slope, but as we just talked about, you can always flip the equation around so you get a slope between 0 and 1. So have your slopes between 0 and 1 here and fill in those points. And then we walk along the edges. So that given those points now, we now know for each of these edges from edge to edge in this dimension of the triangle, we now know, originally we only knew the attributes at these 3 points. We now know the attributes, color value, what have you, at each of these points along the edge, and we just walk from edge to edge. These now become a series of horizontal lines that we can then walk from left to right and apply the same approach. There's a slope associated with that, right? So for that color gradient value here, we would now know the correct red channel for this and the correct red channel for this, and we can walk along that edge and interpolate accordingly. Mike asked a good question about, how do you find, for commercial GPUs, exactly how these things are done? It's generally not, or it depends. It's up to the manufacturers to kind of decide how much of that information they want to release, how much of it is published in technical reports or academic publications, and it really depends on the culture of that particular group at that particular point in time. So I was being pretty specific with what I was saying. I didn't have a definitive answer for, which is specifically for triangle fill hardware, how that is done in 2020. I guess we're 2021 era GPUs. And I said conflicting report because you'll see blog posts from NVIDIA engineers that say one thing and something else that says something else. So maybe it depends on which GPU you purchase, what type of hardware you get. Seems unlikely to me, but I don't actually know entirely how it's done. But ultimately, algorithmically, it looks fairly similar to what we have here. It's not fundamentally different from what we were doing here. To me, the big question is still, as I mentioned, whether NVIDIA, for example, is using fixed function hardware to do this kind of work. Because it's still very amenable to fixed function hardware. That's our MP2 that you're all 20% done with right now. Or whether they're realizing that they might as well just spend more resources on shaders, just have more shaders, and just pick off some of the shader cores and have them apply this. Because it's also something that can be done very easily in software. It's also very amenable to that type of approach as well. I know some of you will start frantically Googling trying to find a definitive answer. Feel free, and we can share that on Discord, and that would be great. I guarantee we can find some conflicting information, and that's where I left off my search. So that edge walking approach for doing triangle fill is appropriate, and it makes sense in terms of applying the same exact algorithm to what we were doing for filling in the lines themselves. There's a lot of weird special cases or edge cases with lines, specifically with regards to when we're doing triangles that are next to each other, right? When we draw two triangles as part of a triangle strip, for example, the expectation is there's no gaps between those triangles, right? That's the whole point of having a triangle strip. You're guaranteeing this strip of triangles, but that edge walking approach may not round consistently, and you may wind up with gaps. So the truth of the matter is, and I think you'll see this is also the case as you implement MP2, algorithmically it's pretty clean and straightforward. In hardware, you'll be spending the most of your time over the next 7 days, I guess here, simulating edge cases, discovering edge cases, and then simulating those edge cases. The quicker your teams get into that flow of things, where hardware we think is pretty good passes all of our existing simulation inputs. And again, the simulation input doesn't have to be that much, right? It's just 3 points. Feed that in and see if you're getting fragments out that make sense, right? This iteration of hardware, team thinks the hardware is pretty good, testing on the board kind of works and then fails spectacularly. tracing that failure case back to a new set of inputs you can provide for your hardware in simulation, and then finding and correcting those edge cases while not accidentally, adding new bugs as you fix those old edge cases. That's going to be a pretty, I think, pretty common iteration place your team is going to be in on this MP2. You really need to get there soon, though, I think, because I think you'll find a number of those. Each of those would then involve a build for the board, an FPGA synthesis run. So each of those tests is a good hour, right? Rounding up a good hour of your life doing each one of those tests. I don't know how many of those edge cases you'll discover. Depends on how carefully you design things in the first place. 10 would be my guess. So you need to have enough time to be able to have that much flow of simulation, sign off on a board run, get results back, usually through the ILA is the best way to figure out here's the input that breaks our hardware, add that to your test suite, test again, iterate, fix, and all that. 10 of those would be my guess. The actual testing of that would be 10 hours. And then the actual design and implementation depends on how efficient you are at doing that. Long story short, there's edge cases. Um, that edge walking approach doesn't explicitly say how we calculate what the equations for the line are. We always know how to do it via calculating from 2 points the point slope form. There's also the implicit form for a line. And the nice thing about the implicit form for the line is in elementary school, you may have learned that, given 2 points, you calculate A, B, and C to get AX plus BY plus C equals 0. The truth is there's many multiples of those that also are valid equations for that line, right? You can multiply it by any value and still get an equally valid equation for that line. So the nice thing about this implicit form of the line equation is we can set up C such that we don't have to do division to calculate that implicit form for the line. And then similarly, given 3 points and the three resulting lines, and this is exactly what we're doing in MP2, or very, very similar to what we're doing in MP2, given those 3 points, 3 points and the corresponding three lines, those three equations for lines are basically subdividing the two-dimensional space into two half spaces, right? Of above the line or below the line. We're doing it in terms of the areas of the resulting triangle, but it's the same exact concept. It's really an identical concept. The math works out to be exactly the same, but we're above the line or below the line. So in determining whether or not a point is inside our triangle or not, given 3 points, three vertices, excuse me, and a new point, we would just have to determine, are we consistently at the same point above or below the line for all three of those lines? And you can set up your A, B, and C such that it always has to be greater than 0. And if you get greater than 0 for all three lines, then you have a point that's inside that triangle there. I'm visualizing just that a little bit. So for our edge equations, for any line equation, you split your two-dimensional space into two, right? That's the actual line drawn through the middle there, AX plus BY plus C equals 0. Then you have all the points that are above 0 and all the points that are less than 0. So we can then take that, and given three vertices that comprise a triangle and the three corresponding lines, we can then define our triangle as just as the intersection of those three half spaces. Given the first line here, A1x plus B1y plus C1 equals 0, we can define all the points that are above that line, all the points that are above this second line here, as well as all the points that are above this third line here, as being the points that are inside that triangle. This may look arbitrary, what is above, what is below the point, just like how we're having to reorder our vertices when we're doing our triangle setup in MP2. And I was expecting lots of questions about that and haven't gotten to that. You haven't seen any yet, so I don't think you've gotten to that point yet. We may also have to then reorder our vertices here. We have to do so consistently because we can't change the orientation of our triangle, but we may have to change which point is the first vertex, which point is the second vertex, and which point is the third vertex. And if you do so consistently, you can get the three half spaces to correspond to then the interior of that triangle. So our math becomes not easy, but in terms of what we have to calculate, we don't actually have to calculate the actual line equation here. Just like when we're doing the Bressenham's line rasterization, we just have to calculate the sign of that equation, which tends to be a simpler thing to do than calculating the equation itself. There's some initialization condition where the area would be equal to 0, or the slope of that would be equal to 0. The sign of that would be equal to 0. And then as we increment in our x or in our y dimension, it's much easier to calculate the change in that equation versus just calculating it for an arbitrary value in the equation. This should start to sound kind of familiar for those who did dig into the MP2 pre-lab. We're doing something nearly identical to that for MP2. I think what you're going to see is really the difference in this type of class, right? The difference between just explaining this in a PowerPoint slide and having to do it in hardware. I think that's and I, hopefully that's the value of a class like this, right? So in terms of a introduction to computer graphics class, this topic is completely done. Okay, this is what you do. You've done it and you've learned how it works. But in practice, your task is to actually implement this in hardware. And it's really hard to fool hardware, right? Hardware will find your edge cases for you if you send enough data into it. Hardware will find enough places to lock up and break. Um, and I think hopefully that's the value of this course. So algorithmically, we formulate it slightly differently by using the area equation versus just the edge equation, but it's very similar. All three of these have to be greater than or have the same sign, but have to be greater than 0 or equal to 0 for the point to be inside the triangle. We're doing the same exact thing in our MP2 hardware. In practice, I'm expecting a lot of questions that haven't happened yet. Um, I don't want them all to be Monday at 10 o'clock, so at PM. So do me a favor and try a little bit today. Obviously, you're going to try tomorrow, and try to find a little time before Monday at 10 o'clock. I will help you at Monday at 10 o'clock, but I don't want to have to wait that long for the big picture questions. So we got that. So given our half spaces, we can define what is inside our particular triangle. This approach doesn't explicitly say, much like the Stefan rasterization algorithm doesn't, it separately has to say how we actually walk through the triangle. For the traditional edge walking approach, um, the approach taken is to just set up a bounding box. And which points are we trying to determine if it's inside the triangle or not? We're really just trying all of them. So that's the idea of the bounding a box. There are many different ways to traverse a triangle. Even if we're using the approach that we're doing in MP2, where we're stepping in the x or y dimension always by 1, there are edge cases, no pun intended, of the triangle, or special cases of the triangle in which it's still really nice to have a bounding box. In this case, the explicit approach is calculate the bounding box, which is a pretty easy thing to do with comparators. Find the minimum x value of all 3 points, the maximum x value, the minimum y value, and the maximum y value, and just try all those points. At least it's nice and straightforward, right? In that approach, it's bounded by the shape of the triangle. You're never going to miss a point if you do that bounding box, right? You're guaranteed to eventually get to all the points that you have there. This issue of orientation is kind of the other special case here. The winding order of the triangle does matter. We at least just have to be consistent with how we're calculating things. The same approach will work if you do the clockwise ordering of the points in our triangle. That may look backwards on your screen, but anyway, it looks correct to me. The clockwise ordering of points in your triangle and the counterclockwise ordering, as long as we're consistent with which one we were doing. If you do it in the opposite order, we're looking for all the values being less than 0 than greater than 0. But it's the same exact triangle. You'll get the same exact points back out. You just have to check the initial order of that triangle, because those are technically, although we haven't seen this at all yet, those are technically two different triangles. This triangle ABC is a different triangle than ACB. They look the same. They describe the same thing in our two-dimensional space here, but in three-dimensional space, those are technically two different planes, right? One has a normal that's a surface normal that's coming out of the screen. One has a surface normal that's going into the screen here, and that does make a difference, right? When we're going to calculate the lighting, what shade this should be if there's a light source in here, knowing which way it's facing is important for that. So we have to be consistent with how we're doing that. It should result in the same potential fragments. At least right now, it should result in the same exact fragments being generated, whether it's clockwise or counterclockwise. And Brian, absolutely, your question is right on. So as a potential optimization, if we were doing this in software, I think that would be a good potential optimization, right? Instead of trying all 3 lines, try them one by one. And the first one that fails, you can stop trying the other 2. In hardware, we could also do that. If you look at how we do the edge testing or the area testing in our MP2 hardware, we're trying them all in parallel. So there's less value in stopping after we get all the results right away anyway. So we don't have that micro optimization. But if they were serialized, those edge tests, then there would be an advantage to stopping early if we were doing it in sequentially way. So We have to then, for this edge walking approach, calculate A, B, and C. We can solve for A and B in terms of C. There are infinitely many values, A, B, and C, that satisfy those two equations. Computer engineers will be required to take linear algebra in future catalogs. You should still take it anyway. If this is a topic that you enjoy and you're learning more about machine learning and computer graphics, and you still need another elective and you can take linear algebra, you should take it. It will eventually be required. But this is very basic, high school level algebra here. We can set up the linear system. We can calculate the matrix determinant, or the inverse here for the determinant, and then we can set C to be x0, y1 minus x1, y0, the diagonals of the matrix, to then get a relatively straightforward way to calculate what A and B should be for a somewhat arbitrary C. So for those 3 points, we can set our initial conditions for A, B, and C. Calculate now for any new point that comes in, whether the resulting equations are greater than 0 or less than 0. So it's very similar to what we're doing in MP2. It is not exactly the same approach, but there's an initial kind of setup approach, right? Given 3 points, 3 vertices for our triangle, set up the math, right? Do the triangle setup. Determine the edges for all of our attributes, but certainly for determining whether it's inside or not. Determine the edges between those. Basically, our 3 line segments that we have here. That's our triangle setup, or our line equation setup. For the edge walking approach I'm describing here, there's an outer loop. And in the outer loop, we're going from xmin to xmax and from ymin to ymax. For each scan line in that bounding box, and now in our inner loop, do that determination, right? Check if the pixel is on a scan line, or if all 3 edge equations are positive, emit that as a potential fragment. Spit out set pixel or some sort of set fragment equation in your algorithm to say, yes, this is a valid fragment we're interested in here. Let's take a couple minutes as a class. I don't think breaking into the rooms, unless you think otherwise, I'm willing to try it again. But I didn't think breaking into rooms worked all that well on Thursday. I'm trying to get the equivalent analogous circumstance to turning to your partner and working through this with your partner. At least today we'll have time to kind of report back. So your in-class exercise for today, and it's a relatively straightforward one. At least personally, I still find it easier to reason about this type of optimization from an algorithmic or software perspective first, and then worry about the hardware implications second. But this would be naive isn't the right word. This would be a straightforward implementation of the edge walking approach. There's an initial fine bounding box function. Of course, we properly pass things by reference and all that. And then there's a setup equations function that calculates A, B, and C for the 3 lines here. And then we have our outer loop traversing in the y dimension, inner loop traversing in the x dimension, and then we're calculating the value for the 3 edges, which is A0 times x, B0 times y plus C0 for A, B, and C for those 3 lines. And only if all 3 of those values are greater than 0, then you set pixel, right? You emit this as a, is valid fragment is our output here. And so we go through all of these and do all of these here. And I think we can assume for sake of argument that we can ensure that for A0, C0 through A2, C2, that checking if the value is greater than or greater than equal to 0 is an appropriate thing to check for that case here. So what I want you to do is, it's a little bit abstract, but taking this as an input, you've been provided this source code or this algorithmic breakdown for how to do the edge walking implementation. We could think of it from a hardware perspective, but I think that would probably take a bit more time. Think of it just from pure software. How could we do this more efficiently? And I will break you into groups of 3 because we do have enough time to come back and kind of collect results. And if the person you're in the room with is not awake, let me know. I do understand that you cannot see this slide while you're broken into the room, so everyone would then need to pretty quickly go to Canvas and just grab the Learning Module 4 slides there and have those open, and just come up with an approach. Just sketch it out, piece of paper, come up with some ideas as a team, and then we'll report back in. Let's give it a solid 10 minutes here. So take a look at this. You're going to get a room full of three other folks. I'll try to make it rooms of four here. One of you at least has to share the slide and have the slide available, or at least copy paste this pretty quickly, and then report back in about 10 minutes. Questions about this before I spit you out into rooms? Okay, we're gonna do it. We're gonna do 7 rooms, and I'm not gonna let you choose. Enjoy. Well, if you have time, Steve, why don't you join room 7? Can I move you to room 7 here? They're down a person. I don't know how to. I don't actually know how to do that. I'm gonna figure that out. Hmm. I guess so. I wasn't able to move you over effectively, so. Now this is still being recorded here, Steve. But yeah, I mean, I used to present that as well. I think this is probably sufficient to talk about the different approaches that can be used. But yes, there was a version of this that was shortened for trying to keep the length reasonable that had that as well. Is that how you learned it back in the day? Turns out that this whiteboard is not the best way to do code entry. All right, let's try something else. That ain't working. All right, people are matriculating their way back in. It looks like there's still some heated discussions going on, so I think people don't want to leave, but they have no choice in about 30 seconds here. Um, I find that extremely painful. All I can see is that there's people in breakout rooms doing something, and I don't know. Anyway, compromise. We're compromising here, but hopefully we came up with some good things. So as people are making their way back, we didn't all make it back here. A couple folks are still just hanging out, but now they're done. Okay, so everyone is back now, or making their way back now. Does anyone want to report out? There's a lot of different ways we can optimize this code. Um, you know, different perspectives in terms of how you do optimization. I think it's always good to look at it algorithmically first. Like, mathematically or algorithmically, what are we trying to do? And can we improve upon that? At least that's always been my philosophy. And then from there, well, first off, let's back up. We want to first decide, is it worth it to optimize, right? That's always the first question we want to answer. Well, here it's worth it to optimize because I asked you to. But in general, right, the question we have to answer is, what do we gain? What do we lose by applying that optimization? We always lose something, right? There's always some cost of optimization, and that cost is time, design time, right? Implementation time, not meeting your original schedule or budget or whatnot. Oftentimes, there's other trade-offs involved in that optimization as well, be it software or hardware, code complexity, tooling complexity versus resulting performance. In hardware, we often have explicit trade-offs of resource usage and performance. But okay, assume we've answered the question of yes, we should optimize. You're told you have to. It's your job. Okay, fine. I think it's always important then, given that as your explicit goal, is to understand the performance, both in kind of the big O notation sense of the word, but then also in terms of actual runtime performance. And then you can start to look at, algorithmically first, what kind of things would make sense to do slightly better, slightly differently. And then you can also look at, for the same exact algorithm, what kind of, you can call them just code optimization, software optimizations, or just performance hacks may make sense. They're all part of the same approach here. But usually you get better benefits from algorithmic changes than from code hacks. One can change the big O complexity of the problem. The other tends to just change some constant factor associated with it, but both can combine together to lead to really great performance improvements. There's a lot of different ways we can do this, and the things you came up with in your breakout rooms, which I had no visibility into, maybe quite or may not be complementary to each other. We may not be able to apply all of them at once, but I'm open to suggestions. What can we do to make this code better? You can speak up. You can type in the chat. Either is fine by me. I hear you. Kind of an early termination of the loop, or not of the loop, but of the checking, right? And that was Brian's point from before, right? Which was, if one of them is less than zero, then we're done. We don't actually have, something seems wrong. Okay, then we don't actually have to do all of them, right? If one of them, yeah, I wouldn't doubt it, Matt. I'm curious to hear what you came up with. That's a perfect optimization to start with. So if we're worried about, it's a micro optimization, but if we're worried about the actual computation that's happening here, and that, let's assume that floating point math is kind of the slow part of this approach, we're cutting down on it by some amount. It's hard to say exactly how much, because it's hard to look at a triangle and say how many times E0 is going to be less than 0 versus E1 versus E2. Maybe we can traverse the triangle in such a way that E0 would be less than 0 more frequently than the other two, but that at least would improve upon the edge cases of that performance. Other thoughts. So that's great. We can manipulate this code in lots of ways. So Matt, what did you have in mind? Nope. Well, that sounds it's roughly what I was thinking in mind as well. I'm the only part I didn't really get a good feel for, and it'll be hard for you to share images as well, is um what it means to change the bounding box. So you're saying, okay, we start with we I understand sorting because we may want to do that. We have to keep the relative order of the points though, right? We can't change the order of the 3 points or the equations breakdown, but um, we can sort in terms of which one we start with. Take a look at your screenshot here. Not yet. I can't. Okay. Let's see. Okay. Okay. All right. So for this triangle, why don't you walk through it one more time? So between this one and this one, we can do a bounding box. This is X min though, right? So it saves us not having to go all the way to X max. You're saying because we know we can stop here. Okay. Oh, that's what you meant by covered. Okay. Yes. All right. All right. So thanks, Matt. I get that. So that's a nice approach. I think you're really onto something with that approach. Ryan's counterpoint is good. That yes, you have to when you have a new idea, you have to try a lot of different weird shaped triangles. That's been my discovery over time. That so many approaches work well for nice, boring, fat triangles that just kind of sit there and look very triangle-y. Isosceles triangles work for any of these approaches. Try some really obtuse ones and see what happens. But that seems like it would work. But I'd have to think about it a bit more. In general, the type of approaches I think that would look good for this, that would work well for this, and what I'd like people to do would be, post on Discord in general when you have time. If you came up with something different as a team, we're not going to have time to go through all of our examples here. Couple of things that I think you should see. So first off, what you mentioned, Matt, your team came up with something along those lines makes sense in that we have these three edge equations. We don't necessarily always need to test all three. That's one point. I agree with that. Second point you came up with, which I would have done a little differently, but makes some sense as well, that we actually learn a lot as we go in either the X or the Y dimension. That at some point, even if we take the bounding box, we go from outside the triangle to inside the triangle to then back outside the triangle. And once you've done that, you'll never go back inside the triangle. Right? There's no holes inside the triangle. So that should be a pretty significant optimization. And then the final thing I think a lot of teams would probably come up with, but I'm curious to see what you're able to post and do so on Discord, is this math, which if we thought the point slope form was too much or the slope intercept form was too much math, this is certainly too much math for our rasterization. There's the absolute value of it, but the change of it as we go in the X or Y dimension is bounded, right, by simple addition. So that's what we're doing in our MP2 as well, right? We have the initial values for E0, E1, and E2. But as we go from X to X plus plus, the change in those edges is just a constant addition, and that would be a pretty significant performance improvement as well. So different combinations of that is also sorts of things I was wanting to see you come up with, and it was nice to see that the teams enjoy that challenge. That shared breakout rooms doesn't work so well for me. I'm just sitting here, not twiddling my thumbs, not really sure what to do next. So we'll experiment with that approach as we have a few more of these going forward. But hopefully that kind of inspires the group a little bit more to dive into the weeds of MP2. I heard from a couple of you who told me a couple direct messages saying, yes, we're actually fine. We just haven't coded it up yet. It'll take some time to do that properly. I'm looking forward to seeing your results. But otherwise, let's leave things here for today. I'll have my office hours if you have any questions today. And otherwise, I'll see everyone in lab tomorrow morning.